Your love, it is my truth, and I will always love you, love you.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
You're telling us, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting it done.
Alright, so today we are going to continue our discussion on the memory hierarchy, especially the cache part, and we are going to talk about why we have cache misses and what are their remedies. But before we start, again, this is the big picture of computer architecture. I don't think I have to tell you exactly how the computer works, but one thing that you have to keep in mind is that memory is a big part. And because memory is a big part in this modular architecture, so the performance gap between processor and memory actually cause a lot of performance issues if we don't find a way to address that. So in the hardware side, we address the gap between processor speed and slow DRAM is through building SRAM-based cache, and we also make it multi-level. So in this way, we can assure that most of the time we don't need to access DRAM. However, a lot of you might be thinking, why having a small cache would help. And the reason is we have localities in your code and data. To capture this locality in your code and data, we have investigated different ways of building your cache. And turns out that the best way of building it is through this weight associativity cache, in which we organize cache blocks into sets. And each set may contain multiple blocks. And you can consider a set is like a hash entry. And whenever you have a memory address, we partition the memory address into 3 fields. The offset, which indicates the location of the requesting byte or the requesting word within the block. And a set index, which is the hash result of your memory address, indicating if the cache needs to be in a cache, or if the data is in a cache, where in a cache can we find it? And by where, it means which set. And the remaining ones are the tag, which is the identification number of each cache block. So with this, whenever we receive an address, we partition it and use the set index. We find the right set of blocks that may contain your data. And however, remember, this is just may contain your data. So to make sure it's 100% there, we need to compare the text that's associated with each cache block to make sure that some of them is identical to the ones that are you looking for. If you cannot find anyone that is a match, then it's a miss. Otherwise, it will be a hit. So that's the basic idea of accessing the cache. And if you remember, the idea of set is like a hash. So the reason why we build them as multi-way is because we want to avoid the collisions that you might have in a cache. So with the idea of cache, what happens when you are performing an access? So if you are writing data, first of all, you might issue a store instruction from your processor, and again, we partition the address into these three fields, and if we find it's a hit, then this is a write, so we would just reflect the change of the word within the block and set the block as 30, which meaning that this place right now has the most up-to-date data of the particular memory address. And then if it's a hit, then we are done. However, if we cannot find this stuff in the cache, then typically what would happen again? You may have to find a block location to accommodate the incoming block. However, if the block that you are going to replace is a dirty block, right? Which means that the current position is the only place in a computer system that has the up-to-date data. So you must reflect that change to other places, which is the lower level memory hierarchy. So the operation of reflecting a change to a lower level memory hierarchy is called write back. So you write back the victim block which you are going to replace into the lower level memory hierarchy, and then fetch the block that you desire to that location. However, if unfortunately it's a miss again in the L2 cache, you have to go through the same process until you find a block, and then repeat the process like write and set 30 at the L1 level. If you are having a read, it's again the same, that you will issue a load instruction, and if the block that you are replacing, if it's a hit, then you just finish the operation. If it's a miss, and if the block that you are replacing is a dirty block, you have to write it back and fetch the incoming block after you finish the write back process, and again until you find a block and you finish all the write back operations. So, and the reason why we need to know this is because we want to know, well, if I have a piece of code, what the performance looks like on the target architecture. And you might feel like, oh, how do I know how many sets do I have? How do I know how to partition the memory addresses? So I give you a very quick formula, C equal to ABS, for that purpose. First of all, the C is the capacity of your cache. The A is the weight associativity, and B is the block size, and set, S is the set numbers. So with that, you can easily write that the number of bits that we need in block offset would be log 2b, and the number of bits that we need in a set would be log 2s, and the tag would be the total address length minus log s minus log b. So that's the application of C equal to ABS. So with that, the last lecture we have been simulating a two-way cache and then we figure out that, well, for this two-way cache, we have a 50% miss rate. So that's where we were, and today we are going to continue our discussion. So you must remember that in the last lecture, we practiced the C equal to ABS on the NVIDIA Tegra X1 and Intel processor. Right, so you know the cache configuration of them looks like this. You know the address configuration of them looks, the address partition and will look like this. And both processors are actually in production, and you can find those machines. And today we are going to have demos on these machines, but it's really important that you need to remember the C equal to ABS matrices and then apply it in the code and in the problem that we are asking you. So the first one, we will start with Tegra X1. So given this Tegra X1, given this is the code that we are going to investigate today, can you tell me the data cache miss rate of this pieces of code? wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looking at what you guys thinking. Okay, so there are quite a few popular answers, but why don't you go ahead and discuss with your friend in 90 seconds. Do you have a pen and paper?
Not an extra one.
Okay.
I have a pencil and paper.
Sure.
A equals
You all write down your name here. Can I borrow that pencil? Thank you. Put your name down here. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so looking at the result after discussion, we have this amount of response. Okay, so you might be curious about like why we are passing this sign up sheet right now, because looking at the previous result, it seems like it tells us that we have 54 people participated, but actually I just counted at the time that the number of people we have here, it was only about, 35 at that moment. So definitely there are 20 other people are ghosts somewhere. So I would definitely want to figure out who is actually around, and for others who is actually not here but try to put in poll. I think that's kind of like a cheating, right? Agree? Okay. All right. So for this question, right? So after the second vote, it seems like most of you still thinking about the answer is B and C. So how do you get the answer? So to solve this kind of problem, what is going to be the first step? What's the very first thing to do you would like to do if you want to address this problem? So this is what kind of problem? What kind of problem is this? What is the purpose of this problem? Like, what are we asking you to do? No. Are we optimizing anything? So what are we actually wanting you to do? Like, we are asking you to evaluate the miss rate, right? But how do you evaluate? Haven't we done something similar to this just a few slides ago? is cache simulation, right? So if we want to do cache simulation, what do we need to know? You need to simulate the behavior of your cache, right? But how do you simulate the behavior of your cache? What's the very first thing a cache would do when we receive a memory request? What was that? What was that? If you receive a memory address, then what's the next step? What was the word? What? Find index and offset, right? So, and also the tag. So it's partition, right? It's partitioning your memory address. So to know how to partition your memory address, what should I be doing? Yes? C equal to ABS, right? Oh, sorry. So with C equal to ABS, what's the C of this cache? 32 kilobytes. What's the A? Four-way associative. What's the B? 644 byte block. And what's the S? It's an unknown, right? So we have to solve the unknown. But after solving the unknown, we know as the right top side, right, there are 6 bits in the offset, 7 bits in the index, and the tag bits are the remaining bits, right? So, with that, now, what to partition? The memory address, right? How do I know the memory address? What's the very first element that I could access? I should access according to the code. According to command, what is the very first thing that I'm doing here? Load A, right? So if now index I is 0, what's the address of A0? What's the address of A0? 10,000 in hex, right? So the very first address is 10,000 in hex. So now partition this 10,000 in hex, right? What I will get is that a tag equal to 8, an index equal to 0, so hit or miss. Is it hit or miss? Is it a hit or a miss? Is it a hit or a miss? Miss. Why? What can you tell is a miss? Because right now, this is the very first element we access for this pieces of code, right? So nothing is in there. So this is a miss. Okay. So if that's at the very beginning, do we have anything in the cache yet? So are we going to replace anyone? No, right? So there's no one being replaced. And the next element will be B0, right? So what's the address of B0? What? What's the address of B0? 20,000, right? So partition it again. We will find the tag is 10, the index is 00, hit or miss? Miss. Okay. And are we replacing anyone? No, why not? It's the same index as the previous block, right? We're not replacing anyone. Why don't we replace anyone? Why are we not replacing anyone? Enough cache size? There is what? It is the cache what? What do you think? You don't know? So, if the cache is full, right map cache, do I have to replace anyone at this point? If it's a direct map, same set. Do I have to replace anyone if it's direct map? What's the meaning of the map? It means that there is only one block associated with each set. That's called direct map, right?
So if
I have that kind of cache. Do I have to replace anyone? What? Why not? But, okay, what's the meaning of direct map? No, it's 1 per set. Alright? So who tells you if it's a different set or not? Which number tells you if it's a different set or not? The tag, the offset, or the index? Which tells you the set the block should be? What? Index, right? So, it actually has the same index with the previous one. So to replace it or not, we have to figure out how many blocks are there in the index already, and how many blocks can a set with that index accommodate. Which parameter tells you that? How many blocks within a set? Who tells you that? What? No. Is it capacity? Is it capacity related? Thank you. Is it related to your capacity?
Is it set associated?
It's a set associativity cache. So it's the set associativity, right? So if you look at this cache, it's a 4-way set cache. So what does that mean is that for each index, we can have up to 4 blocks sharing the same index in a cache. So what does that mean is that even though my cache is super empty, but if there are more than 4 blocks that needs to compete the same index, unfortunately, only 4 of them going to win. Right? This is not a perfect match problem. Right? So it's not about capacity. It's more about the set associativity. So there could be a case like that. Right? But for this particular case, because this is just the second block that we try to put into the set, and the set can accommodate 4 different blocks. So we can actually place it in this set index without picking anyone off. Okay, now, I have C coming in. What's the address of C0? What? 30,000. So partition it, tag 18, and index 0. Hit or miss? Miss. But do we need to replace anyone? No. Why not? This is just the third block. Alright? So now I have D0. What's the address of it? 40,000, partition it, 200, hit or miss? miss. Do I have to replace anyone? No, because the set can accommodate 4 blocks, right? So now I have E0. What's the index? 50,000, partition it, 28, index 0. Hit or miss? Do I have to replace anyone when I want to have this block in?
Yes.
Why? Because there we can only accommodate up to 4 blocks within a set, given this is a 4-way associativity cache. At this point, we have to kick out A0 to 7 because the last time we fetched A0, we have the whole 64 byte in, right? So when some of you say that the capacity is enough, that's not accurate. Because at this point, the cache only have 4 times 64 byte, which is 256 byte in total. But the cache capacity is 32 kilobyte. The capacity is way more than that. But we start to replace stuff because this index 0 is now out of its capability of accommodating more blocks. So we have to kick this out. So now, what's the next element we are going to access, given we have already gone through A, B, C, D, E's zeros? A1. What's the address of A1? What?
10,001.
10,001? This is a double number, right? So how wide is a double? 8 bytes. So what's the address now? 10,008. Partition it. The tag is 8, index is 0. Hit or miss? Hit or miss? It's a miss because when we get the E0 in, A0 and until A7, they are all kicked out. They're all kicked out. So the first row, this is not in the cache anymore. Right? So this is going to be a miss. And we have to find another victim block to replace this one. And according to LRU, that will be B0 to 7. Okay, now I'm accessing B1, 20008. Partition the address like this. Hit or miss? Miss. Do we have to replace anyone?
Yes.
Who?
C.
Okay, so tell me what's the overall miss hit rate? Miss rate? 100%. Right? So if you go through this one, this is a code that looks so normal that you will write. However, the miss rate is 100%. The answer is E, not B, not C. The answer is E. 100% of them are going to be missing. Seriously, are you kidding me, Professor? So, we should have a demo. It should be this slide. Okay, here we go.
It's okay.
Okay, so here we are again. So we have went through a lot of different things and how blocks are stored. Okay, so this is the partition of data address as the last time, and this is the code. Very similar to what I show you, right? But I added this, well, essentially the same, right? It's EI equal to A times BI plus CI divided by DI, right? The only difference is that here I print out the address, so you know that I'm not bullshitting you regarding the memory location. And now I'm running this on a Jetson Nano, which exactly use the Tegra T1 processor. And by the way, Tegra T1 processor is the same processor architecture that you can find in your Tesla if you have one. So if you write these pieces of code on your Tesla, that will be terrible. And the last time I drove a Tesla, I hate it, to be honest. I doubt they have code like this. Okay, so the demo here, we are using a program called Belgrind. So the Belgrind has a tool called CacheGrind, which allow you to profile the memory behavior. And the format of Belgrind is you run a Belgrind command with a space. Well, there are many tools in Belgrind. It's a debugging and profiling tool. And one of the tools called CacheGrind, so you have to specifically tell Belgrind that you are using CacheGrind. And then run the program and with the argument. And here I'm passing the argument as the size, and I guess that's the orientation. And so what I'm doing here, so for this, and it's kind of interesting because the Belgrind can only profile the miss rate of the whole program. So what I'm doing here is, in the first run, I only profile the code without running that specific loop that I am doing here. So right now, by using this zero argument, I'm actually bypassing that loop. So what do I get is the basic cache miss rate when I do not have that loop. So the next round, if I add that loop in, the difference of the number would tell you what's the additional memory accesses and cache misses incurred by this one. So let's run it without a loop. And without a loop, here is the total number of cache misses, cache access and misses. It tells you I have around 1.5 million of data references, and within this 1.5 million, only 8.5K they are misses. That's without that particular loop. So this is the this is typical. This is the process of initializing that array. Now, let me run this loop and see what the performance looks like. So after I run this loop, I got around 20K more accesses, but I also got around 20K more memory misses. Did you see that? Did you see that? So we can put them in a mass, right? So that's the good thing about Jupyter Notebook. So this is actually the total number of memory accesses before the loop, and this is after the loop. And I can put the number of cache misses, which is 8543. That's before running the loop. And after running the loop is 29033. So the math here is counting the difference in the number of accesses and the differences in the number of cache misses. So, and also we have, so with that, right, you can see the cache miss rate is 1. An evidence that everything there is a mess, right? Isn't that surprising to you? Isn't that surprising to you? That everything is a mess here, right? So sometimes when you write your code, you don't care about how many times in your life have you ever been caring about your cache configuration when you write code? No, right? But this example tells you it's actually important, right? If you have a processor like Tegra X1, this code looks elegant, easy to understand, but it's terrible because everything is a cache miss. Okay, so here we have the demo tell you the cache how to use Belgrind. Now, I have another processor from Intel. What's the cache miss rate would look like for this piece of code if I run this on an Intel processor? Alright, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now looking at, okay, I like this graph, right? It means that we definitely need some discussion. So why don't you go ahead, discuss with your friends to figure out how to address this one. Go!
Let me look. Okay, so it's gonna be, I'm assuming it's gonna be pretty much the same. So we do A0, B0, C0, D0, E0. When it's E0, because there's 64 by blocks. But we don't have to just, okay, so keep going. So now we go A1. A1 is not leading to the place. But is it a miss? Because I thought, do we have like A0, A7, all this?
Yeah, there's all the first one.
Yeah. So now five and one. So then I'm assuming like for the next E1 C1 and then like everything until you get to A8 You have to replace.
No, because I clicked it.
I think let's do this. No, but I thought like the way we replaced was like this gets 64 bits because it's like when you saying like what we replaced is A0 for A7. So I think when we did this and it was this, we got first A0 not just A0.
Alright, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, are we going to see some magic? Okay, nothing too different. But it seems like more of you are leaning toward A now. So can some of you share your thoughts about the answer? What do you guys think? Okay, you are avoiding eye contact with me. Alright, I need a better friend. I remember I have a good friend. What do you think?
Since it's 8-way associativity, we should have 8 misses at the beginning and then
8 misses.
5 misses.
5 misses at the very beginning.
Yeah. And then for the next, because it's a 64-bit block, next 8 we will get a hit. So it should be 1 of 8.
1 of 8. Okay, so that gives you the answer of 8. Right? That's what you're saying.
Yeah.
You're so smart. But that's difficult to understand. I know how you get it, right? But you know, as a teacher, I have to walk through the whole process. Do you mind to walk through the whole process with me? Okay, so this is an Intel Core i7 cache, right? So according to the partition we just learned for this cache, it has 64 4 sets, which give you 6 bits of offset, 6 bits of index, and 52 bits of tag. So the very first access first memory access we will perform is on the address of hex 1000, and that's for A0, right? With that partition, we will get tag 10, index 0, hit or miss. Miss. Do we have to kick out anyone from the set? Probably not, right? How about the next one? Are we going to access A1 or B0? B0, right? What's the address of B0? Hex 20,000, right? And if you're going on, it's a miss. Do we have to kick out anyone? Okay, so we can fast forward this because it's probably the same, right? How about this? When we do E0, right? The last time we have to kick out someone here, right? But here, after partition, it's still the same index. Do we have to kick out someone? No, right? So this is, so thinking about this, right? The set associativity is like how many bedrooms are there in your apartment. If you only have 4 bedrooms and if you want to accommodate a 5th resident, you should kick out one person, right? You are not supposed to use the living room, by the way. But here, right? For the cache, 1 bedroom can only sit 1 block, right? It's not like our real human being. But with 8-way associativity cache, you can think about now every apartment have 8 bedrooms, so you can have E0 here without any problem. So it's still a miss, but we don't have to kick out anyone. So now when we access A1, partition the address, it's still the same index. But is it going to be a hit or miss? Hit, right? Because this one and this one, they have the same index and a tag. And this one is not kicked out here, right? So this is a hit. So if you repeat this, if you keep repeating this, right? See, I spent a lot of time doing this. All right. Uh-oh. No, don't crash. Oh, lovely. All right. Yeah, that's the problem with too many animations. Okay, so far it's all hit, right? Now, when I entering 8, if you partition the address, the text remains 10. However, the index changed, right? And right now, if you look at the index 1, do I have someone named 10? No, so it's a miss again. Right? So if you keep repeating this, you will find, as you said, we have 1 miss out of 8 memory accesses for each array. And we have a total of 5 arrays, which means that we will get 8 misses per 40 misses, or say 1 misses per 8 misses. So the cache miss rate would be 12.5%. All right. So that's why you need to learn C equal to ABS, right? Because it's helping us solve problems like that. And you know, okay, this kind of code is safe to write on Intel processors, but it's not a good practice on NVIDIA processors. And some of you might ask, can a compiler do any optimization on that? The answer is no, right? Because when I compile the code on the NVIDIA Tegra processor, it's already highly optimized. And you still see performance like that, right? So it's a good enough evidence that some of you might think, a lot of software programmers might think, oh, the programming language, the compiler can do a lot of stuff for you. But the answer is they won't, because they can't. All right? So here, the miss would occur when the array index is a multiply of 8. So the total number of cache misses would be 12.5%. Okay, so it's significantly reduced from 100% to 12.5% if you are able to build an 8-way associativity cache on your processor. However, building such a cache with highly weight associativity is actually pretty difficult to build in terms of the hardware. So that's why a lot of people will say, well, ARM architecture is better, but if you're not companies like Intel, you're not going to build a good ARM processor. Which turns out, and a lot of people might think about the architecture matters a lot, especially when Apple talking about like we migrate from Intel to ARM architecture and we show the performance benefits. But to be honest, like what this demonstrates, it's not about architecture, it's not about instruction set architecture, it's not about x86 or ARM. More stuff, more performance are actually related to your data cache behavior, your data cache organization. I cannot tell you too much about the Apple processor design because they never tell other people about that. But one thing I can tell you for sure is that Apple processor is good in its memory hierarchy design, not in microarchitecture design. So don't be fooled by those commercials because that's not the real cost. All right, we talked about cache misses, but why do we have cache misses? So there are 3 types of cache misses. The first one is called compulsory miss. Aaron. Do you know you know, this is definitely not. Let me try again. Okay. Aaron, by any chance you know what is coherence miss? No. Have you ever heard coherence miss before? No. Right? This is an example of compulsory miss. Right? How can the cache ever know something before the memory access is even triggered? Right? If you have never previewed the material, if the topic hasn't been brought up, there's no way the stuff could be in a memory, could be in a cache by default, right? So this kind of miss is called compulsory miss, which is the first time miss in your code. So the first time you access an element or a cache block, it's typically a compulsory miss, right? The second type is called capacity miss. Because capacity means that the working set of the code is so big in a way that there's no way I can accommodate everything you need unless I change the bigger cache size. That's capacity miss. That's a capacity miss. The third type is probably the most frequently seen miss. It's called conflict miss. So it happens when the data block that I am looking was previously in a cache, but it was lost now for some reason. And that reason is typically because the set cannot accommodate more blocks. So your block gets kicked out. So that's called conflict miss, because multiple blocks are conflicting in the same set index, and I cannot accommodate all of them. That's called conflict miss. 3 different types of miss. Okay, so let's go back to this direct map cache that we have simulated in the last lecture. So in the last lecture, we talked about how to generate a direct map cache. You should remember, right? We partition the address. Here's the tag and index. So for the first memory access on A00, hit or miss? What type of miss? Compulsory miss. Why does this go compulsory miss? First time, right? Compulsory miss. How about B0? Compulsory miss again, right? So when I serve A0, I put A00 and A1 in this cache. And now when I serve B0, it's still the same. If you look at the partition of the address, right? It's still the same index, which is 3, right? So I will go to this one, and I will kick out this 2, and put B0 and B1 in, right, to serve this compulsory miss. Now, when I'm accessing A01, what kind of miss? What kind of miss? What kind of miss? Alright, 1, 2, 3. Conflict miss, right? Why is it a conflict miss? Because previously A01 was there before, right? Look at the animation. I do have A01 here before, but someone kicked me out, right? So it turns out that would be a conflict miss. Now, when I access B1, what kind of miss? Well, hit or miss. What kind of hit or miss? Miss. What kind of miss? Okay, 1, 2, 3. Okay, I love that voice. Right? It's conflict miss. Now, when I'm accessing A02, hit or miss? What kind of miss? One more time. 1, 2, 3. 1, 2, 3. Why is it compulsory? The first time we access A02 and A03, the block, right? So it's a compulsory miss. Now, when I'm accessing B2, hit or miss? What kind of miss? 1, 2, 3.
Compulsory.
Be confident. 1, 2, 3.
Compulsory.
Compulsory, right? Because that was the first time we accessed B23. Now, when I'm accessing A03, right? It's a conflict miss, right? Because A03 was there before, but because I want to accommodate B23, so you get kicked out, right? So, as a revenge, I will kick out B2 and B3 to accommodate A03 and A02. So it turns out if you repeat this pattern, right, for the direct map cache, in the first run, we know it's 100% miss. But now you know within this 100% miss, only 50% of them are compulsory miss, and the other 50 are conflict misses. And if you look at the utilization of this cache and the size of data that we are traversing, right? So we are only traversing 10 elements for now, right? So it's a 20 elements per array. 20 elements in total, and each element is only 8 bytes. So it's 160 bytes in total. That's way smaller than the cache size because the cache can accommodate a total of 256 byte data. So there's no way those misses are because your cache are too small. So a lot of people were thinking that, well, if I want to address the cache miss issues, then increased capacity would solve every problem. The answer is no. Because most of the time, right, if you look at this piece of code, none of them are actually capacity miss. Which means that increasing the cache capacity does not help at all. Right? So that's why you need to know what are the causes of your cache misses. All right, for two-way cache associativity, two-way set associativity cache, we partition the address and simulate it again. So now for A00, hit or miss? Miss. What kind of miss? Compulsory. Okay. And when I accommodate A00, I will put A00 and A1 because they are the same block in the cache. Now, for B0, hit or miss? What kind of miss? Compulsory, right? So when I need to accommodate B0, I have to accommodate them in index 3. And right now, fortunately, I have another entry in index 3. So I can put them here, right? So when I access A01, hit or miss? When I access A01, hit or miss? Hit. Why? It's here, right? So this is a hit. When I access B1, hit or miss? Hit, right? Now, when I'm accessing A02, hit or miss? What kind of miss? Compulsory miss, right? So if you keep going, you'll figure out with two-way set associativity cache, you can eliminate all conflict bases, even though the cache size remains the same. Right? Magic. Okay, so now, looking at this, can you tell me why there are so many cache misses in NVIDIA cache Tegra X1? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, according to the first round of the vote, it looks like we definitely need some kind of discussion. So why don't you go ahead, discuss with your friend for another 90 seconds, and let me know the answer later.
So I remember that when we get to like A8, it's going to be another compulsory miss, not a common compulsory. Because A8 is going to map to a different spot. Yeah, exactly. So that would be a compulsory miss. Right, because 4 last time was compulsory and then a conflict. Okay, so every single one, so when we get to A8, it's going to be a different so B0 X. But then eventually we get to B1. Because basically you'll do 4, I believe, and 5 X1 pieces, and then that's it. Or like 8, I guess. Because then it's
All right, let's wrap up in 15 seconds.
Yeah, so that was 8, so then you get a case. That you get the math into the
5,
right?
4, 3, 2, 1. Time is up. Okay. So after discussion, woohoo! See, that's the power of discussion. So most of you agree is D. But there are still quite a few don't agree is D. So I need someone to convince others. That's democracy, right? The majority has to convince others this is the right way to go. Otherwise, we cannot move forward. What?
They don't have to convince if they're already a majority.
Well, in theory, they should, right?
Well, yeah, but
Okay. You know, there was one advice I got when I become a professor is that people tell me, don't talk about politics in the class. Now I know. Okay. So, any idea?
I didn't work out math for it. I did say D, but I didn't work out math for it. I figured the compulsory misses happened pretty early on in the beginning. They never happen again, and so most of them are conflict misses, and so most of them.
So your God's feeling tells you it must be D.
Yes.
Okay, I like your intuition.
Yeah.
Okay, what else? So he is actually a trained machine learning model, right? You just give him the input without knowing why, but he can tell you after the inference result, it looks like D. That's good. I like your intuition. What else? That's another model solver. Any heuristics? Okay.
So we know that it's for sensitivity, and we already know the first four will be compulsory misses, and everything afterwards, but until the eighth byte is all gonna be compulsory misses. So that's like.
Yeah. So because only for 1 out of every 8, right?
So I got
Right. I should have this place somewhere. Why is that not showing up? Score 7. Okay. So, I will make up that slide, but if you go back to NVIDIA Tegra 1, right? This first 4, they are compulsory misses. These first 4, they are compulsory misses, right? But when E0 kick out others, itself is a compulsory miss because that's still the first time we access E0. But when we kick A0 to 7 out, the next run of accessing A1, this one would actually be a conflict miss, right? And it goes on and on until we reach A8, right? So only 1 out of 8 in this sequence is not a conflict miss. Everything else will be a conflict miss, right? So even though it's 100% miss rate, but there are still differences in this 100% miss rate. So if you put that math in, only the first couple ones, they are compulsory misses, but everything else, they are conflict misses. Now, let's go back to this one, our lovely Intel processor. Okay. Do you mind to tell me the answer to the same question on the Intel processor? Yes?
We still have the same poll as the last question.
Okay, let me try to fix that. How about now? Give me a second. Is this the same one? Okay, let me try again. This is the constellation angle 2. Okay, let's try. How about now? Alright, let's wrap up in 15 seconds.
It updated to the right poll, but then it locked.
Really? How about now? Still locked?
Oh,
Now it's refreshing.
Yeah, now we're waiting for it to
Ah, boy.
now it's on the old question.
It's now on the old question? Anyway. Alright, we dropped 50% of them, right? So it doesn't matter if you miss one. Alright, looking at this. Okay, wrong question, apparently. So, why don't you discuss with your friend within 90 seconds?
Oh, yeah. I don't remember. Yeah.
Unless you're like, but even if you like do something is like you're done with using
Like it's probably cheaper to use
Alright, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, E is more popular than others, but you know, it's even less than 1/3. So, can someone in E convince others? So what's E? So the answer of E is 100%. 100%. How can you convince others? Anyone would like to give it a shot? Alright, Aaron's friend.
The only misses we have are the ones where we're originally loading in all the data.
Right.
So that is 1 out of 8, and we don't have any other misses until we need to load A9 through.
Right. So if you look at the behavior, right? A1 is not even a miss. So the remaining miss we have is simply because the first time we have to load each block in a cache. So meaning that the only miss you're going to see are compulsory misses, which means that 100% of them are compulsory misses, right? So for the Intel processor, if you want to further optimize the performance of this pieces of code, is increasing the cache size help? Why not?
Because you don't have any capacity.
Because you don't have any capacity miss. Is making the cache more with associativity helpful? More than what is currently now? It's not. Because we don't have any conflict misses, right? The only thing you have to think about is that how can we improve compulsory misses for this pieces of code, right? So if you don't understand what's the root cause of your main cache misses, you're not going to do the right thing, right? So it's important to do the right thing, right? Do the right thing. Right, I mentioned it several times. All right, so that's why we need to know the cause of cache misses so we can take the right approach when we optimize our cache. So for this particular question, would you mind what's the right thing to do to address each type of miss? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so like this, look like we have a normal distribution, right? So why don't you go ahead and talk to your friends in another 90 seconds.
Because when you do this, you have to take I was even take that for it. But it seems like that would make sense. And if you retrieve more things, that takes longer. Maybe it's like all like in like
It only loaded 0 to 7. 7 is large.
That was the one I said, so I was like one chapter of the section of where it was like associated the most important block first. Or the most important chunk first. We'll send that all loading down. So it's not only that you did take that into account. But if we set up a position that it's wait, increasing sensitivity? No, so actually decreasing just don't know what, but it's easier to find it. Like there's only one second.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Still kind of normal distribution, but maybe that's really the answer, right? So let's see. What do you guys think? So we have compulsory conflict and capacity misses. We have ABCs. Now we want to connect them together. So can increasing associativity reduce conflict misses?
Yes.
Yes. You have seen a sufficient amount of examples, right? When we simulate two-way caches versus direct map caches, when we simulate Intel processors versus Tegra processors, it's all about associativity, right? So the first one is a yes. How about the second one?
No.
How about the second one? Why not? Because you saw the hint I gave?
Because when you have higher associativity, you have to check more tags to
Mhm.
find a hit.
Alright, so here's the thing. The associativity does not come without an overhead. There's no free lunch in the world, right? There's no way you can sit in a class but get a good grade, right? Even though you want to cheat, you still have to spend time copy past, right? So there is no free lunch. Same thing as set associativity. You have to check more text simultaneously, which means that you need to add more boxes within a cycle. So it's going to increase your cycle time. So that means every time when you perform the cache access, it takes more time, no matter it's a hit or miss. Because whenever you need to check the text, you need to compare them, you need to multiplexing them, there will be an overhead, right? So how about increase the block size? Can it increase the miss penalty? Can it reduce compulsory misses? What's the drawback? What's the pros of adding the block size? Fewer compulsory misses, but why?
Well, like we saw in the example,
Mm-hmm.
we loaded in 0 through 7,
Mm-hmm.
and then their next compulsory miss was because we were trying to access 8, so
Mhm.
we had a larger block that loaded 0 through 8 or higher.
Right. So here's the thing, right? If you increase the block size, every time you have a miss, you can fetch not only 8, but maybe 16. Right? But what's the cost? Is it a free lunch? What's the cost?
Anytime you miss, you have to bring in larger
More stuff, right? So every time when you have a miss, you have to fetch more data, which means longer miss penalty. Right? So three of them are correct, right? 1, 3, and 4. Okay. All right, so this is the hardware solution, and in the next lecture, we are going to talk about not only the hardware solution, but also the software solution. And the software optimization will probably be one of the most important things that you should know as a programmer. So I don't think a lot of hardware stuff would affect your life, but the software stuff would if you're a programmer. So definitely don't miss the class next on this Thursday. So we still have a reading quiz due next Tuesday. As usual, I will pull up the reading quiz later today. And again, if you miss one reading quizzes, don't send me an email because we won't allow any makeup, any extension. They are designed for preview, so it becomes meaningless if we do it afterwards. And it's also unfair to others. And assignment 2 is up due next Thursday, so start early. And again, we hate any kind of cheating on anything. So if you cheat, we will give you zeros for the cheating item. And for people who didn't show up today but actually pretend they are here today, we have the name of people here. So for you guys are safe, but for others, I think their first half of because I would give the attendance grade every half of the quarter. So the first half of them will be 0. So if they really don't want to show up, they don't need to show up until midterm. All right? So I will see you on Thursday.